In this video, we're going to look at another example of separable differential equations. In a series circuit containing a resistor with resistance of R ohms and an inductor with an inductance of L henries and a battery that produces a voltage E of t volts, Kirchhoff's second law states that the sum of the voltage drops across a resistor V is equal to IR and the voltage drop across the inductor V is equal to L di dt, the sum of these two voltage drops is equal to the supplied voltage E of t by the battery. So L di dt, this is a voltage drop across the inductor, plus this is Ri, which is a voltage drop across the resistor, is equal to E of t, which is a voltage of the battery. And the initial current I of 0 is equal to I0. This differential equation models the current I as a function of time. So basically our goal is to solve for I as a function of time. All right, let's look at an example. We have a 24-volt battery that's connected to a simple series circuit in which the resistor R is equal to 12 ohms, the inductance L is equal to 2 henries. Find the current I of t and also find the limiting value of the current as time grows to infinity. Assume that the initial current I of 0 is equal to 0. So what we're given is L is equal to the inductance is 2 henries. We have the resistance, the resistor is 12 ohms. And the battery, E of t, is equal to 24 volts. So when we look at a circuit like this, we can see that as you go around the circuit, the general convention is that if we go from a minus to plus, this is a voltage gain, but we take that as a negative because in a circuit there is usually more voltage drops than there are voltage gains. So voltage gains are actually taken as negative, voltage drops are taken as positive. So we have minus E of t plus, now the voltage drop across the resistor is IR, and notice we lose voltage, voltage goes down, but we take it as positive. Plus, the voltage drop across the inductor is going to be L di dt, and according to Kirchhoff's voltage law, the sum of the voltage drops going around the circuit, the sum of these voltage drops is equal to 0. Now, if we bring minus E over to the other side, we get the same expression that we had in the last page. So we get IR, which is a voltage drop across the resistor, plus L di dt, which is a voltage drop across the inductor. The sum of these two voltage drops is equal to E of t, which is a voltage supplied by the battery. All right, so our strategy is to apply Kirchhoff's voltage law to set up a differential equation for I of t. Once we have a differential equation, we will separate the variables, then we integrate both sides, and we find the current I of t, I as a function of t. So the voltage drop across the resistor is going to be IR, the voltage drop across the inductor is L di dt, and the voltage supplied by the battery is E of t. And according to Kirchhoff's voltage law, we have IR, voltage drop across the resistor, plus L di dt, which is a voltage drop across the inductor, is equal to E of t, which is the voltage supplied by the battery. So this is Kirchhoff's voltage law. In the context of the question that we have the resistor is equal to 12 ohms. We have the inductor, L is equal to 2 henries. We have the battery voltage, E of t, is equal to 24 volts. And we have the initial current, I of 0, is equal to 0 amps. Amps is, I guess, the unit for current. So we get 12I, putting it into the equation, 12I plus L, which is 2 di dt, is equal to E of t. E of t is the voltage supplied by the battery, is 24 volts. I of 0 is equal to 0. We now have an initial value problem. We have a differential equation that involves the current I, and we have the initial current, the initial condition, so we're going to now solve this differential equation for I of t. All right, so we have 12I plus 2 di dt is equal to 24. The initial current, I of 0, is equal to 0. Let's isolate di dt, so subtract 12I from both sides and divide by 2, and we're going to get di dt is equal to 12 minus 6i. Let's rearrange this to solve to separate the variables. So we have di divided by 12 minus 6i is equal to dt divided by 1. So now we have all the i's on one side, I is the current, and all the t on the right-hand side. Now that the variables have been separated, we can integrate both sides. How do we integrate the left-hand side? We're going to apply U substitution. Let's write this down, U substitution. We let u be equal to 12 minus 6i. Differentiate both sides. du is equal to the derivative of 12 is 0, so we get minus 6 di. Solving for di, we get di is equal to du divided by minus 6. So through integration, U substitution, the left-hand side becomes log of 12 minus 6i, and we divide by negative 6 because of the reversing the chain rule, because of this minus 6 right here. And the right-hand side, integral of dt, well, integral of 1 dt is just going to be t, reversing the power rule, t plus c. Now let's isolate the log function. We get log of 12 minus 6i, multiply both sides by negative 6. This is equal to minus 6t minus 6c. And let's call minus 6c c1, so let c1 be equal to minus 6c. So we get log of 12 minus 6i is equal to minus 6t plus c1. All right, so we have log of 12 minus 6i. I'll rewrite this so we can work with this equation on this page, is equal to minus 6t plus c1. Now exponentiate both sides so we can get rid of the log. So we have e to the ln of 12 minus 6i is equal to e to the minus 6t plus c1. Let's now separate out the exponentials using the exponential law. So that reduces to e to the minus 6t times e to the c1. So notice the constant that was additive becomes multiplicative. That's because of the exponential law. E and log cancel. We get absolute value of 12 minus 6i is equal to e to the c1 times e to the minus 6t. Now we get rid of the absolute value, and we're going to get 12 minus 6i is equal to plus or minus e to the c1, e to the minus 6t. Let's introduce another constant. Let a be equal to plus or minus e to the c1. So we have 12 minus 6i is equal to a e to the minus 6t. Now let's solve for a. We have initial condition I of 0 is equal to 0 because the initial current is 0. That means when time equals 0, when t equals 0, the current I is equal to 0. Let's use that to solve for a. So we get 12 minus 6 times I, which is 0, is equal to a times e to the minus 6 times t, which is 0. So we get a is equal to 12. All right, so what we have is 12 minus 6i is equal to 12 e to the minus 6t. Now let's isolate I. We get minus 6i. Let's add or subtract 12 from both sides. We get 12 e to the minus 6t minus 12, and divide by minus 6, divide by minus 6, and divide by minus 6. So we're going to get we'll get I is equal to minus 12 divided by minus 6, that's plus 2, and 12 divided by minus 6, that's minus 2 e to the minus 60. We now have the current explicitly as a function of time. So we have I of t is equal to 2 minus 2 e to the minus 60. Now the question asks us to find the limiting value of the current as t goes to infinity, as time goes to infinity. So let's take the limit of I of t as t goes to infinity. That's going to give us 2 minus 0, because the limit of 2 e to the minus 6t is 0 as time goes to infinity, as t goes to, because we have a negative exponential. This is equal to 0. And if I was to elaborate further, it would be 2 divided by e to the 6t. We can rewrite it in this way. Limit t goes to infinity, so you're dividing by a huge number, because as time goes to infinity, e to the 6t approaches infinity, and we have infinity in the denominator. The ratio approaches 0. So the limiting value of the current is going to be limit as t goes to infinity of I of t is equal to 2 amps. So let's illustrate that from the graph. Notice that the current starts at 0 at the beginning, at time 0, and as time increases, as we go around this circuit, we can see that the current increases to a value of 2, and 2 is a limiting value. It can't exceed 2. So this is the graph of I of t is equal to 2 minus 2 e to the minus 6t, and we have shown that as t goes to infinity, I of t, the current, approaches 2 amperes. All right, thank you.